Welcome back to statistics. So it's time to start putting together some of the ideas that we've seen over the course of our study so far. Today, I'd like to combine two ideas. One is the idea of random sampling and the statistics that you can compute from a random sample, like sample means or medians, standard deviations, and so on. We'll actually focus on sample means here. And the second idea is the idea of a distribution of a variable. So a distribution, as represented by a histogram or a dot plot or something like that, gives you the possible values of a variable and the frequency with which it takes on those values. So the way we're going to combine those ideas is in the concept of a sampling distribution. So the idea is if you take a sample and you measure a statistic from it, like xBar, the sample mean, you've got to realize that the value of xBar you observed was just one of many possible xBar values that you could have observed had you just taken a different sample. And so to understand the xBar value that you did observe, it's important to have some idea of the set of all possible xbar values from which it came. And the sampling distribution of xbar gives us just that, the distribution of all possible xbar values from all possible samples. So let's take a look. So introducing sampling distributions. This is going to be kind of a conceptual uh, set of slides, and then we'll move over to our SALT tool and take a look at some examples. Let's first think about the idea of a simple random sample. So the idea is that all groups of the same size have exactly the same chance of being selected for the sample. So we start out with some population consisting of all individuals that we'd actually like to observe. But of course, it's impractical usually because that's a very large group. Uh, However, we would be interested in a parameter like the mean value of whatever variable we're talking about across the whole population. We denote that mean by mu in statistics usually. Since we can't know the whole population, we can't usually know the exact value of mu. So what we do in statistics is get a sample, a random sample, and we observe the sample statistic from that sample. If it's means we're talking about, that would mean the sample mean x bar. So x bar would be the mean of the individuals in the sample. And the idea that we'd like to pursue is using x bar as some kind of estimate for mu. But in order to do that, we need to realize that the X bar we observed came from the sample that we picked. And there are a whole bunch of other possible samples out there. And each of them comes with their own X bar value. So here's one, here's another one, here's another one. And all these X bar values are not going to be the same. In fact, there's just oodles and oodles of possible samples and possible X bar values that come with them. And if we wanted to, you know, figure out how much we trust our X bar value, we need to know where it sits in sort of the spectrum of all possible X bar values. One way to get an idea about this is to take all the X bar values that could be generated from all the different samples and throw them all into a histogram. So that's what we've just done. That histogram that's formed out of all possible X bar values is called the sampling distribution of X bar. And the sampling distribution of xbar tells us both the possible values that xbar can take on and the frequency with which it takes on each of those possible values. So, with that as sort of a conceptual introduction, let me do a little experiment here, first by hand and then with the aid of a computer, to sort of try to make these ideas a little more concrete. I have here in my hand grades from a class I taught several semesters ago. These are final averages on a scale of 0 to 100. And it was a pretty small class, so there was only 14 individuals in the class. But I've recorded all their final grades here on slips of paper. And notice all the pieces of paper of the same size. And so I can what I want to do is try to estimate the average final grade from samples from this population. So I'm considering these 14 grades here, I'm considering them my population. It's a very small population. And in fact, I could compute the population mean mu very easily just by averaging these 14 numbers. I don't want to do that though because I want to illustrate how we can estimate mu by using samples. So what I'm going to do is I'm going to take my favorite hat here and I'm going to put all these slips of paper in the hat and I'm going to shuffle them all around and mix them up. And I'm going to draw random samples of size 3 from this population and use those to compute sample means xbar. So I'm drawing now. Here's the first individual drawn. That's a 77. Shuffle them up again. Here's the second individual drawn. That's an 88. Sorry, an 89. I'll set that aside here. And here's the third individual drawn. That's a 75. So I'll set that down here. So my first sample of size 3 from this population was a 77, a 75, and an 89. So from that, we can calculate a sample mean, 77 plus 75 plus 89 divided by 3. And we get a sample mean of, can you read that? 80.333, 80 and a third. So the sample mean from my sample of size 3 turned out to be 80.333. That would be, based on just that information, that would be my best guess as to the actual population mean. Now, somebody else might do the same experiment. So I put my 3 guys back in here, and I'm just going to draw another sample of size 3. First guy is a 76, set him aside, shuffle around. Second guy is a 77, set him aside, shuffle around. Third guy is, an 89, set him aside. And we've got our second sample of size 3, and let me just compute the sample mean there. So we have 76 plus 77 plus 89 divided by 3. The sample mean now is, probably can't see that, but now it's 80.666. So when we draw different samples, we get different xbar values. That's pretty easy to see once you think about it. How much do we trust those xbar values? Do I trust the 80.333 more or less than I trust the 80.666? Well, we really can't say right now because we don't really know the sort of whole spectrum of values from which those came. So we'd like to see the sampling distribution of xbar in this case in order to get that idea. Where did the values I drew sort of sit in the spectrum of all possible xbar values? Fortunately, we have software that can help us see this. And I'm going to pull up Salt right now, and I've already gone ahead and loaded precisely that data into Salt. So here you see the first 10 of those 14 scores in my population. And we can go ahead and take a look at sort of the graph. This is a histogram of the population data. Showing all 14 scores. We could see a dot plot too. There's a dot plot of all the 14 scores. So that's actually the population. But again, we want to kind of pretend like we can't see that, and we want to approach this by looking at samples. So I'm going to go to the sampling tab in Salt and essentially repeat the experiment that we just did, except many thousands of times, so that we can begin to see what the sampling distribution of all possible xbar values. So the first thing I'll do is choose a variable. There's only one variable here. And then Salt brings up a couple of dialog boxes here. First, the number of samples, and then the sample size. I was drawing samples of size 3, so I want to make my sample size 3 instead of 4 here. And I'll just go ahead and leave the number of samples at 100. Now, when I press the green button here, Generate Samples, what it's going to do is it's going to generate a sample of size 3, compute its xbar value, and throw it into a histogram, actually a dot plot. And then it's going to repeat that until I have 100 xbar values all in a dot plot. And by doing that, I'll be able to sort of build up this sampling distribution for xbar. So let's give it a try. Here we go. Bang. So there's 100 samples. Each dot in the plot here represents a sample of size 3, and the value is the sample mean. So out of those 100, we had 1, 2, 3, 4, 5, 6 that had a sample mean of 77. And you're beginning to see here the sampling distribution of xbar, of the sample mean when you draw samples of size 3. So I'm just going to continue drawing samples of size 3 and adding 100 dots to the plot each time I click the button here. And we're now beginning to see the sampling distribution of xbar. You begin to see an order and a form taking place here. The sampling distribution of xbar is basically unimodal. And the majority of values are concentrated, it looks to me like, between essentially an area around 76 to 82. The two samples I drawn by hand were 80.333 and 80.666. Those would be in these two bars here. So those were fairly typical. But if I had to guess the center of the sampling distribution for xbar, I would think something more along the lines of, a little bit bigger than 78. In fact, the center of the sampling distribution for xbar is given right below the dot plot. It's right here, generated samples mean. Turns out to be 78.7 essentially. So that's about right here, right where this kind of highest bar is. That's the actual mean of all these 2,800 xbar values that I've generated in this simulation. 78.7. So the sampling distribution of xbar itself has a mean that's about 78.7. Now, there's another thing I'd like to point out about this sampling distribution, and that is the shape of it is quite a bit different than the shape of the population distribution. If I go back here and look at my charts and graphs, look at a histogram, for instance, the population distribution has an asymmetrical shape, but the sampling distribution has a roughly sort of symmetric shape, almost sort of a normal-like shape. These are facts that we're going to see over and over again, and as we study sampling distributions, we're going to uh, we're going to focus on the things that sort of remain constant for sampling distributions, no matter where the samples came from. That turns out to be a really interesting topic. Another thing I'd like to point out is goes back to again this idea of the center of the sampling distribution. The center of the sampling distribution for xBar turned out to be about 78.7. If you look down here, you see our original data again. Here's a histogram for our original 14 observations. The binning is a little different than in the previous histogram I showed you. But check out the mean of my original 14 observations. It's 78.7. The exact figure is given to 5 decimal places, but I want you to compare the mean of the original 14 observations here to the mean of the sampling distribution, this 78.6928238. Those are very close. The mean of the 14 is 78.71, and the mean of the sampling distribution is 78.69. They're the same to 1 decimal place. This is not a coincidence. It turns out that if you could get all possible samples inside this sampling distribution, those two numbers would be exactly equal. What we have a sort of motto or slogan in statistics that this goes by, and that's that xBar is an unbiased estimator of mu. The true mean was 78.7. The mean of the xBars was 78.69. And again, that number would get even more and more close to the true value the more xBars I put in that sampling distribution. So the mean, on average, in other words, on average, not every single time, but on average, observations of xBar are on average equal to the true mean in the population. And that's why we call xBar an unbiased estimator of mu, the true population mean. So this has been a little quick introduction to sampling distributions. There's a whole lot more to say here, and we'll begin saying it in our next video. So I hope you found this helpful, and I will see you next time. Y'all take care.